Welcome to Instruction Tuning with Hugging Face. After watching this video, you'll be able to explore how to load a dataset and format it, describe model creation, and training arguments. You'll also be able to define collider and training loss, and describe pipeline for text generation. Instruction-based fine-tuning is referred to as Instruction GPT. It trains the language models by following specific instructions to generate appropriate responses. Here, dataset plays an important role by providing structured examples of instructions, contexts, and responses. Using this approach, the model handles various tasks effectively. The context and instructions are linked together to form a single input sequence for the model to understand and use to generate the desired response. Let's first load the code Alpaca 20K dataset, a programming code dataset. This dataset includes the components such as instruction, a unique task description for the model. The input is an optional context or input for the task present in about 40% of the examples. Lastly, the output is an answer to the instruction. Next, split the remaining dataset into 80% for training and 20% for validation. Here, let's drop the samples that contain an input value. For fine-tuning the dataset, it is important to pre-process the data by creating functions that generate the prompt. For training, the formatting prompts func function uses the dataset as input. For every element in the dataset, it formats the instruction and the output into a template with the format #instruction, followed by #response. Adding end of the sentence or EOS token at the end of the text indicates that the model should stop generating text at this point. Finally, the formatting prompts func no response function acts similarly to the formatting prompts func, except that it doesn't include responses. This function prepares samples for response generation when validating the model. For creating a formatted dataset, a code block generates instructions. The first code block strips and tokenizes the input. It splits and tokenizes the responses for evaluation. The second code block defines a list dataset class obtained from the dataset and creates a torch dataset from the list. This class is useful in generating a dataset object from the instructions. Let's fine-tune Facebook's OTP 350M model by loading a base model from Hugging Face. You can use a parameter-efficient fine-tuning or PEFT method, low-ranking adaptation or LoRa to save time and convert the base model into a PEFT method suitable for LoRa. Next, fine-tune LoRa by defining the LoRa config object from the PEFT library with specific parameters such as LoRa rank, target modules, and a task type for causal LLM. Apply this configuration to the model using getPEFTModel, converting it into a LoRa model. For training the model, define supervised fine-tuning or SFT config. The output directory defines the location for the model and training files. You can customize the number of training epochs and batch sizes for training and evaluation. During training, the evaluation strategy defines the time for evaluation. Set the evaluation strategy to evaluate after each epoch completes training. The max sequence length controls the maximum length of the output responses. Set FP16 to true for efficient training to enable 16-bit floating point precision. Now define the collider. Using the data collider for completion-only LM from the Transformers Reinforcement Learning or TRL library that prepares data batches for training language models on text completion tasks and masks the instruction part of the input when calculating the loss. Additionally, the collider helps add padding tokens for shorter sequences to ensure uniform length within a batch and truncate longer sequences. It creates attention masks for differentiating the actual instruction and padding tokens to prevent them from affecting model learning. It also helps aggregate sequences by combining multiple sequences into a single batch for efficient processing. Lastly, it helps handle special tokens for managing the batch from start to finish, including padding tokens. Next, to define the trainer, create the SFT trainer object by passing the formatting func to the trainer to handle data pre-processing. Then set the packing parameter to false to not pack multiple short examples. Here, the max prompt length parameter controls the prompt length. Lastly, pass the collider to the SFT trainer. Let's review the data pipeline. Load the training dataset. Next, the formatting prompt function generates the prompts from the elements in the dataset. Finally, the data collider handles tokenization and masking. You can plot the training loss saved during training in the trainer state. Let's explore the pipeline for text generation in Hugging Face to simplify the process by automatically handling model loading, tokenization, padding, and text generation parameters. To evaluate the model's text generation, use a text generation pipeline from the Transformers library. First, define the pipeline using the pipeline class with the model and tokenizer. For this, let's set the task to text generation for generating text like a regular chatbot. The max length defines the maximum length of the generated text. Lastly, set the return full text to false, only returns the response without the instruction. Next, generate text by passing input to the pipeline to get responses using functions such as numBeams, which generates higher quality text. The early stopping parameter controls the stopping condition for beam-based methods. Once the pipeline is created, pass the input to generate responses. Here you can see a generated sample response for the fine-tuned model. Finally, let's evaluate the model using the Bilingual Evaluation Understudy or BLUE score. It is challenging to evaluate language models using quantitative metrics. BLUE is a useful metric for coding, and Sacre Bleu is a standardized variant of BLUE. The results show that the fine-tuned model achieves a Sacre Bleu score of 14.7 by 100, significantly better than the 0.4 by 100 achieved by the base model. Therefore, the instruction fine-tuned model generates responses that align better with the expected responses in the dataset. Let's recap. In this video, you learned to fine-tune the base model using Hugging Face. First, load a dataset using CodeAlpaca 20K dataset, a programming code dataset. Format the dataset using the formatting prompts function, which leverages the dataset as input. To create a formatted dataset, use two code blocks to generate instructions with and without responses. To create a model, fine-tune Facebook's Opt350M model by loading a base model from the Hugging Face. Define the collator using data collator for completion only LM to prepare data batches for training language models, and define the trainer by creating the SFT trainer object. Finally, generate a text pipeline from the Transformers library and evaluate the model's text generation using the BLUE score.